Hello, welcome to my channel. I post tech car related content, usually in Unreal Engine or Houdini. This video is about the smoke effect I did. I posted on YouTube some time ago and somebody asked me to show how I did it. So this video is going to show you a quick breakdown so you can also replicate the steps if you want to. The main thing about this effect, as I fly around a little bit to show you, is that it's using a single emitter and a single material for the smoke particles in Cascade, and there is no real-time light involved for performance reasons. I have also a little animation to show you. So what you see here is the light coming in and out of the smoke, and it starts to spin, and the second light comes in, and this is all in a single material. Even though there's two lights, it's just two different inputs in that material. And the animation is driven by a blueprint, which I'll show you at the end of the video. We'll start with how to make the shader. The little bit of story about how I came across making this is that I had to create an effect for a very large scene, and the light that needs to light the particle is very far away and covered a huge radius, which is very problematic in that situation. The first thing I tried to do is, because there was some kind of relationship between the light source and the particle itself, so I naturally think about using the Cascade light module to light my particle, but that does not work. So the light module can light other environment, but it does not light the particle system itself. Even if I use a second particle system with just the light module to light my first particle system with the smoke set to using that a lit material, it will not light this first particle system either. The only option I would have been left with, if I go down a traditional approach, is to put a bunch of real-time lights in the scene. But I really don't want to use huge radius real-time lights from far away to light the smoke. That's very expensive, because the cost of using dynamic lights, movable lights, is its radius and its screen percentage. So in this case, for example, if these two lights, imagine its radius, it's much bigger than what it looks here. It's like probably this size, and the two of them, they will have a radius about probably covering almost half of my string. And because, as I mentioned, the cost of these lights is basically how big of a string area you're covering and how many lights are there. So the more lights you use, the bigger they are. You're trying to render a huge portion of your screen multiple times in order to detect how much of an influence they have, and that's just very expensive very quickly. In this approach, where I fade the light effect directly in the shader, so basically you're skipping the draw course and the rendering course of doing the real-time lights entirely. So it's completely in the shader of the smoke. You don't have to pay all those costs, and you don't have to use the traditional light module in the particle system either. So we'll start with the textures I created for this. As I said, it's just simple smoke material, so I have like a 2x2 smoke texture. I painted in Photoshop, then I generated a normal map in Photoshop as well. Just a little tip on how to generate this: you can use Photoshop's 3D filter, and there is a generate normal map option, and this is the setting I chose for generating my Photoshop normal map, in case you want to do it yourself as well. So it's very soft gradient on my smoke cards directly from this texture. Now, just a quick rundown of my particle system. So the first thing I want to mention is that this particle system really is huge in scale. If you click on the blank back side, you can see here I set fixed bounds of basically 800 meters in diameter of this bounding box. And GPU particle systems will require you to use fixed bounding box. So That's why I set it here, and you can also kind of visualize the bounding box over here. Now, required module, basically just at 10 seconds, nothing special here, 20 spawn rate, and I use the sphere as the spawn location and get the velocity from the sphere by checking this, and use the velocity scale times 100. Basically, it takes the spawn location of each particle in its distance and the direction from the center of the sphere, and multiply that by this amount to give you a kind of velocity. Lifetime, random lifetime range, initial size 200 meters in size. It's really huge. The size by life, what it does, it's very simple. It just it decreases the size gradually over time to like a random range between 0.9 and 0.7, and a little bit initial rotation. Color over life here, the color is constant, it's just 1. Main thing is the alpha, as you see here. This is the alpha curve, so you fade in and fade out. Initial rotation has a small amount of rotation. That's it. That's basically the particle system. The rest of the tricks are all in the shader. So here we go. That's the shader for the whole thing. We'll just like dissect each part of it, so it will not be so intimidating. First off, the shader is set to surface, additive, unlit. You could choose translucent sometimes, but the difference is additive is cheaper than translucent because you don't have to do depth testing. Just everything just added together. That's the cheaper version of particle system, translucent particle systems. Now, first step is to pick a random one variation out of my, sorry, let me close this, out of my 4 different types, and I was just clicking around. So first we take the standard text coordinate and multiply by 0.5. That's basically zooms in, and it will focus on the first one. So you will focus on this one just by this branch, top branch. Then what we need to do is we need to randomly generate an offset in this direction, 0.5 offset in this direction and 0.5 offset in this direction, and combination of those two randomly, you'll get the 4. The reason we have to do that is for GPU particle systems, and usually CPU particle system will use the sub-UV, but the sub-UV module is not supported by GPU, so we have to kind of fix it ourselves. So using you start with the particle random value, you generate a random value between 0 and 1, and this step just ensures that the one side is exclusive. Then we scale that up, so you become a range of 0 to 4. It doesn't exactly reach in 4, it's exclusive on the right side. Then to generate the random combination on the U side, which is the horizontal, and the V side, the vertical, of 0 and 1. And basically we need a 0 and 1 and 0 and 1 and randomly a combination, four combinations, 2 times 0.5. 0.5 is the offset, 0.5, so we need that. The F mod, it takes the remainder. So imagine if you have 3 here, if your random value generated here is 3, you do an F mod, that would give you a remainder of 1. And if you have something like 2 here, you give you a remainder of 0. So the floor here is just because this give you the flow point remainder. Floor here will generate an integer. Here times 0.5 from this is to say if the input value is between 0 and almost 2, it will give you an output 0. And if the input value is between between 2 and 4, it will give you an output of 1. So yeah, that's why we like don't go to 4, because if you have 4 here, that will generate 2 here, but anything less than 4, a maximum it will generate a number less than 2. And if you flat a floor number less than 2, you'll get 1. That's why. Okay, to show that this is working, let's do a little test. We just copy this branch. And let's create a new material here. Real quick. Put it down. You can create a texture with 4 quadrant and 1, 2, 3, 4 on it. But here I'm just going to use a material function, which I created myself. It's a step gradient. This is what it looks like. Let me quickly show you. I will not go into this. Basically, it outputs something like this. So you get the 4 quadrant. You get the saturated corner. You get the orange corner. You get the blue corner, and this faint pink corner. That's basically function as a texture, without me having to draw another texture. So I pump this into the emissive color. I just set this to make it cheap, make it lit, make it to use with particle sprites. Save. We'll go over here to the particle system, go to required module, and choose our new material. Now you can see you got the saturated corner, you got the orange corner, you got the blue one, and you got the faint pink, the pink one. I chose this color scheme because I should test it with the color blind, the not common types of color blindness, and actually this type works. The original gradient Unreal provides, it's typically a green and red gradient, so it can confuse people. Let's go back to our material. So we tested that this UV random picker is working. We don't need to save this. Let me close that. Now next step, what's happening here is I can stop previewing this node. Actually, I need this. So this texture is set to sample type is alpha. Alpha is like a higher quality if you're using black and white texture. It gives you like more precision if you choose alpha. So everything can be sampled directly in one channel in red. So you take the red, multiply by the particle color. In that case, it's just 1, and is multiplied against the alpha of the particle color that we're setting over in the cascade. So this all goes to the opacity. So you'll trim out all the black areas, and you will also fade the colors based on the settings in the particle system. So that's it, opacity. Then for emissive color, basically we're setting all the colors directly here, and the add here is to add together the 2 lights. So in animation, you got a blue light, you got an orange light, and so the orange light, we'll look at the orange light for example. That's just adding the contribution of 2 lights together. And here, the multiply before the add is multiplying between a simple, this is the baseline sort of from shadow to highlight. This is the range you can choose. And the alpha comes from a bunch of factors we're gonna calculate, and I'll show you in a bit. So there's an interpolation between the two, and this is multiplied against basically the light intensity. Now, light intensity use something called the inverse square Falloff. You will see that setting in a lot of Unreal light parameters in the detail panels. It's called inverse square Falloff. It's a realistic way of calculating how much energy you will receive on the surface from a light source depending on the distance between the light source and the point you are trying to draw. Why is it called this name? Is because of because this function. So this is the area function of a sphere. So the area equals 4 times pi times the square of the radius. So what that means is if you have a sphere that's twice the size of your original sphere, that means the surface area of your second sphere is 4 times the area of the first sphere. So imagine you have a light source in the center of these 2 spheres, and the light source is emitting a constant amount of energy in all directions. So distributing that energy at the smaller sphere, which has 1/4 of the surface area, means that each point on the surface gets 4 times as much energy as the bigger surface will receive. That's why the intensity of the light is the inverse square of the radius from the light source. So this is just our setting for the light intensity, and all this part is calculating the distance. The bottom part is calculating the distance. This is the square part, it's saying. So if this is square, this is the radius. So the simplest version is to subtract the distance between the light position. Sorry, not subtract, just directly. You have this node here, directly measure the distance between a light position, which we use a parameter input. Here is set to the world origin, the light position, and the pixel position for each pixel you're trying to draw. That's the distance. So the simplest version is to pump the distance directly in here and square it. That would give you the calculation for the intensity of each pixel. But that will create a problem, which I will demonstrate right now. Is that if I set this to 1, it will make the center very, very intense. That is because our distance calculation goes all the way to the origin. So for pixel that's extremely close to the light source position, which is at the origin of the world right now, it will become very bright. And we don't want something like this. We want like a soft fall off. When the pixel gets close to the center, we want the radius to fall off softly. And because our intensity is derived by distance, we basically need to remap the distance a little bit so that we get that gradient. Now, so how do we do that? The first idea I had is to say, once you reach what we call a light source radius, once your distance touches that source radius, that basically treats anything inside that as a flat radius. So if the particle is anywhere within the source radius, it just treats that part as it flattens it to the source radius. Or if you have so imagine if this line is your distance of the light, sort of as distance is increasing, the distance. Sorry, imagine this is this is your source radius, and this is the trajectory of a potential pixel on a particle. This is your center point, and this is the distance that we're kind of measuring. We're measuring the distance in that axis. So the original version goes all the way to 0 here. So the plateaued idea is to say at the source radius position, we go flat. So you see a plateau here, and then light will become a flat disk. It's also kind of undesirable. So we modify that or get a better result by saying, how about we do something like this? We don't go all the way to the tip, but we kind of diminish that range. That also is kind of pointy, so let's make it one step better by saying, how about we make it diminished range but also curved, something like that. Okay, that's the ideal situation we want to aim for. So let me show you how to do the math for that part. That's basically what this is trying to do. Alright, so we'll jump into Houdini for a second. And don't worry if you don't know Houdini, this is just, I'll show you the functions. It's basically functions and code and describing what we're trying to do. This is the original fall off directly to the center. This is the original distance. This is the remap distance. And the desired result we want is something like that. We want to go not all the way to the tip, but also like a curvy fall off. So this is basically made of 2 components. To remap this, you have a baseline. the baseline is defined by the 1 minus of your fall-off range. So the range here defines the fall-off range in this 40% here. So if your fall-off range is 1, that means you fall off all the way to the original. And yeah, it goes like that. So we use the 0.4 as an example. So this part is the baseline. So no matter even for your particle, if its origin distance like right on the origin, you will still pretend that you're that at least that far away, so you don't get too bright. So baseline here, baseline is the baseline calculation, and the remap distance is baseline times gradient. This part is the gradient. So the gradient is calculated by something in this function. So I'll show you how we arrive at that. To have a curve, you need like an exponential function. This is the shape of an exponential function. In this case, it's just it was an exponent of 2. That's why we have a distance times distance. So that's where we start from. To approach this shape, we know we need a distance exponent. So let me remove this part. I'll show you what this looks like. If I go all the way to the bottom. So you can see if we just square the distance, it will go out of our radius. Our goal is to have when the remap distance and the origin distance meet at this corner. So at the boundary, they should also be both be 2. So this range is way too big, so we need to squash the range in the vertical direction, and we need to find out by what factor we need to squash this range to fit it in this 40%. So what is this distance? This distance is basically the radius times 2. So let's do it here. This will be our factor. In this parenthesis will be our factor. So this is how big it can be. It's radius times radius. This is the current, and the target is the range we want here. This 40% of our radius, so it's radius times range. So this part gives us the factor that we need to squash it in the vertical direction, and you can see here there is a radius here. There's a radius on the at the bottom of the division, so we can remove one. We can simplify this just to radius over range. There we go. So that's the same. So that's the function we arrived at. There we go. So this is just prototype. It just gives us a clarity of what shader nodes we need to arrange. Now let's go over here, back to Unreal. So let me hide this for a second. Now let's just focus on this part for the moment. So this branch, this A here, is our remapped distance. So jumping back here, look at the function. We need baseline times gradient. Look at the baseline. Baseline is 1 minus range times radius. So here, 1 minus range times the radius. That's the baseline. And our gradient is the square of distance divided by radius over range. So the square of the distance divided by radius over range, and add the gradient to the baseline. That is our remapped distance. So all we want here is for the output to be the distance. So what is this contraption doing? This is just to do like, it's a cheaper way of doing if conditions. If conditions can be expensive in the shader if not all parts of your the mesh you're trying to render goes down one branch of the if condition. There's some like lower level GPU optimization theory that means if condition will slow it down if you have parts of your pixels going down one branch and parts of the pixels going down the other branch, which is what we will encounter here. So we will devise this workaround to have 3 branches, 3 possibilities here. And what will happen is that these guys serves as sort of a logic gate, and each time for any pixel, no matter what pixel you are, only one of this gate will open. Because they all output is either 0 or 1, only one of them will be 1, the other 2 will be 0. So when you add them together, that means you only actually just pick 1. Now, how does that work? I'll just give you one quick example. Say we want to have this thing output 1 and these 2 get disabled. That means our distance is equal the source radius. So if distance equals source radius, you subtract that, you end up with 0. And the sign node give you basically the sign of your input. If it's negative, it will be -1. If it's positive, it will be 1. If it's 0, it's 0. So if this is equal, then this is 0, then this is 0. Absolute value is like anything but 0 will be 1 here. And because this is 0, then 1 minus 0 it will be 1. So as you can see in this branch, any number when any situation when these 2 are not equal, this will be 0. And when they are equal, this will be 1, and this will be enabled. Same way works for these 2 as well. Just one more example for this branch. This branch requires the distance greater than the radius. So what needs to happen is when the distance is greater than the radius, this one branch will output 1, and these 2 will turn 0. So if this is greater than this will be a positive number. It will generate 1. When it's 1, it's compare 1 against 0. They will output 1, and if it's negative or if it's 0, it will always output 0. It will disable it. So only when this is a positive number and this is 1 will this branch be enabled. So yeah, only one of the 3 will turn on at one time. You would get the distance depends on. You would calculate your distance with different values depending on how you do it. So now to reiterate, all this part is to calculate the distance and use the inverse square function to calculate the light intensity. Now the second big part is to calculate our backlighting factor and frontlighting factor. So we have these 2, the frontlighting and backlighting added together. And the saturate, what the saturate is doing is to clamp the value between 0 and 1, because we want to interpolate between, it's using alpha, we don't want it to over-interpolate, we just want to stay between these 2, so we do a saturate here. So now saturate is almost free on most modern GPU hardware, so it's cheap to use saturate than clamp if your clamp is just trying to clamp it between 0 and 1. In any case, let's focus on the frontlighting first, which is a simpler version. To explain what the frontlighting means is that we calculate how much light intensity we should output and adjust depending on if the surface of the smoke is facing the light or not facing the light. And we do that comparison by comparing the angle between the surface normal in world space against the vector from pixel to the light. So we have our light here with its light radius. We have our smoke cards. So imagine that the camera is over here. It's a top-down view. So you have the smoke cards. They're bumpy, turning in this direction. Then this is their world space normal. So surface normal. Now these orange vectors are the pixel to light direction, which is what we have in the shader. To find out if a pixel, their normal, is facing or not facing the light, we just do a dot product of these two vectors. The dot product, what it gives us is the angle. So when the two vectors are almost pointing in the same direction, the dot product will be greater than 0. When they are somewhat next to like a 90 degree, it will be 0. Sorry, 90 degree will be 0. When it's greater than 90 degree, it will be a negative number. In this case, it will be almost -1. That's what the dot product will give us. So when it's a negative number, we basically know that the surface is not facing the light. When it's a positive number, the more closer to 1, the more front facing it is to the light. So the more front facing, you get more light. When it's not facing the light, like this side, you get less light. So here, the dot product. Now we also have the option to do a little bit of remap. So what this remap is doing, because the dot product goes from -1 to 1, and sometimes if you don't want the light to, because this whole thing it will be multiplying against the contribution of the intensity. So we don't want the intensity to completely turn off as soon as you reach 90 degree, then you can map the -1 to 1 range to a 0 to 1 range. In that case, we can first reduce the range by half, then at an offset of 0.5. So at this step, it will be remapped to 0 to 1 range. So it just means that if you are in this situation, you still get a tiny bit of light, but not completely black as soon as you reach 90 degree. This is up to your artistic interpretation. Just my implementation here, but it gives you all the options if you want. And then we clamp it. That just means that I still don't want it to go completely black. So I say the lowest I can go is 0.1. So even if you are really not facing the light, we still don't want it to go completely black. Then you times a scale. This just lets you scale the contribution of this branch. Then you add together with the backlighting. Okay, now let's talk about the backlighting. Backlighting basically is the reverse. So it takes the contribution of your front lighting and just times it by -1 and flip it. Since it's just basically the opposite direction. The only behavior difference is that for backlighting, if you look at the smoke here, is that the thicker areas identified by the whiter areas here will be less lit from the backlight, and the thinner areas, which is the blacker areas in the texture, will actually have more light from the backlighting. So we want to add the backlighting and the front lighting together, and we calculate backlighting a bit differently. And as I said before, the backlighting depends on the kind of perceived thickness from the texture, because the original texture does not go to 1, even in the whitest area. So that's why I have a multiplier here to give you a thickness scale. You can scale up the thickness to bring it closer to 1 and increase the contrast a little bit. Then saturate, because this whole branch we don't want it to really go. We want to calculate everything in the 0 to 1 range, sort of in this branch. So we saturate first, clamp it. Then we apply a darken range. What the darken range would do is that it controls what's the maximum amount of darkness you can have. If this value is 1, that means you can go completely black in the thickness area, and we want it to be still slightly bright. So something like that. That's why I use 0.8 here. Then we saturate that. Then we do an inverse, so 1 minus. So use this as an example. If say this is let's say if after the thickness scaling this point is reached 1, then multiply by 0.8. That means this point is 0.8. Then inverse it at this point would 0.2. So the thicker you are, the whiter you are, the smaller this output number will be. And this is all the thickness darkening timed against the angle-based factor. So that will give you the backlighting factor. Backlighting plus front lighting, that's everything. Saturating, saturate, make sure it stays between 0 to 1 for the alpha. Then we get that. Then we multiply against the light intensity. And there you go. So basically 3-bit components. The inverse square Falloff based on distance, just component number 1. Component number 2 is the Frontlighting based on normal. And component number 3 is the Backlighting based on both normal, the inverse of the normal, and the thickness implied in the texture. This part is just a duplicate of the first light. This is the blue light, that's the orange light. Now this part is normal. It's just a little one more thing to cover is to have to derive world space normal from the texture normal and give it a little bit of intensity adjustment. This is the base normal map, and if you loop that between this and the texture, and we basically make it this like more intense than the original is. We have a kind of higher number here. That give you the way to increase or decrease the contrast of the normal, and flip that from tangent space to world space, because our light direction vectors is in world space. So to do the dot product correctly, we need to transform that into world space as well. That's basically it. Now the animation is basically from this blueprint here. We create a dynamic material instance for the particle system and assign it, and the source material is our material instance, and this will create a material instance dynamic, and that enable you to adjust the parameters on the fly. So on the event tag, we can tell the material to change your light position, to change your light intensity, and this branch here is just like after a certain amount of time I start to do the radius calculation to circle them around. So let me replay that a little bit for you. So first you will see this front lighting, backlighting, as the light move front and back towards the camera. Then the spinning, and the second light fading. There we go. Now one more thing I need to mention is that this is not limited to just 2 lights, and you don't necessarily need to add this branch many times to increase more light. One thing you can do, it just like depends on how you set your light position. So instead of fixed light position, we can pick a new light position for every particle, because all this graph executes pixel by pixel. So if each pixel derives a different value from light position, then you can end up with many lights. So that's probably one of the main advantages over using real-time lights, is that using this texture shader thing, you could do multiple lights. So here is one trick to say we subtract the particle's position by the light position. That gives us a vector from the light to the particle. This difference is that this is pixel position, this is the particle position, and we can multiply it by that and create a light at that point. So what that means is this. We can create the direction from the light to the particle. That's the particle. Then we can extend that in this direction and put a light over here, and we can do that for every particle. So let's hook that up and see what that looks like. So instead of having this one static light position, we put it over here. Save that. Now you see here, there's a fake light for every particle at twice the distance from the particle to the particle center. The material itself is very cheap. We're using additive, unlit, the cheaper version of translucent material. And if you look at the instruction here, because it's unlit material, we don't really calculate light maps and everything. And yeah, it's not much instruction at all for this amount of dynamic look. Yeah, that's the end. Hopefully it will be useful to you. in your personal work or your production. And thank you for watching this video.